All right, welcome everyone. Today we're going to look at one more example just to kind of see where things can get a little interesting with power series. All right, so example 5. We're going to do the same thing we've been doing. Find the radius of convergence and the interval of convergence for a given power series. And our power series here is the sum from n equals 0 to infinity of n factorial times x minus 3 raised to the power n. Now, when we look at this series here, let's just make a note here. What is the center for this power series? Well, it's a power series, and it's centered at a equal to 3. This is that number right here. That gives us so we think of that generally as like the center value for our power series. So this is a power series centered at a equals 3. Let's actually look at what happens directly at that center value. And this is going to be kind of true for all of the different series that we've looked at. We could have done this. But we're going to look at it for this specific one. So our center value is 3. We're going to plug this into our series. And let's see what we get. So we're going to get the sum from n equals 0 to infinity of n factorial times 3 minus 3 raised to the n. Simplify that. We have the sum from n equals 0 to infinity of n factorial times 0 raised to the n. And we use a convention here. If we were to write out the first few terms, we would have 0 factorial times 0 raised to the 0. We were kind of writing out the first few terms here. Plus 1 factorial times 0 raised to the 1. Plus 2 factorial, 2 factorial times 0 squared, and so on. And when we look at this, 0 raised to the power 1 is 0. 0 raised to the power 2 is 0. So all of these terms are going to be 0, all except that first one. It's actually going to be 1. So 1 plus 0, and so on. And we can actually do that. We can actually add those up. So 0 plus 0 plus 0, that's something we can do. It's 0. So we end up with the only contribution is from that first term, and it's 1. So the fact that we can actually do the sum here, we can actually find the sum, tells us that this power series, or this series, converges at x equals 3. And this would be true for any power series. We're always guaranteed to have convergence at that center value. Now, one thing that might be a little kind of odd with the notation here, we made note of this before, but 0 factorial we tend to think of as 1, and 0 raised to the 0 we tend to think of as 1 as well. So kind of a notational little note here. But the rest of these are perfectly fine. So 1 factorial times 0 is 0. 2 factorial times 0 is 0. So most of the terms that go on, forever are just 0, identically 0. So we can add those together. And since we can add them together, find the sum, that tells us this series converges. Specifically at this x value. All right, so the question is, what happens when x does not equal 3? So that's the second part of this. We're going to suppose x does not equal 3. And when we suppose that, if x does not equal 3, then the absolute value of x minus 3 does not equal 0. We'll see why that's important in a little bit. All right. So we're kind of breaking this up into two discussions. We looked at what happens directly at the center point. Kind of get this fun adding a bunch of zeros together series. And then we're looking at everything else. So this is what happens directly at the center point. And then we're looking at everything else. And for this everything else, this is where we use the ratio test like we've been doing. So let's do our ratio test setup. So we're looking at an plus 1 over an. Let's fill in what we have. So n, change the n factorial to an n plus 1 factorial when we write out an plus 1. Same thing with the exponent here. That'll be an n plus 1. So we end up with n plus 1 factorial times x minus 3 raised to the n plus 1 all over n factorial times x minus 3 raised to the n. A lot of times when we do the ratio test, we kind of split this up and we multiply by the reciprocal of an, but there were no fractions here. So, we don't need to do that here. We get kind of lucky. We can just write out the one fraction as it is. Now, there's a bunch of canceling that's going to happen. So there's there's n copies of x minus 3 in the bottom. There's n plus 1 copies in the top. So almost everything is going to cancel. We're going to have 1 left over. And then the factorials, we have n plus 1 factorial divided by n factorial. There's going to be some canceling there. And it might be helpful just to remember that n plus 1 factorial is equal to n plus 1 times n minus 1. And we just keep multiplying until we get down to 3 times 2 times 1. And hidden inside of here, right here, that's n factorial. N times n minus 1. Keep going down to 3 times 2 times 1. That's n factorial. So we could think of this as n plus 1 times n factorial. And let's fill that in. So we have n plus 1 times n factorial over n factorial times x minus 3. And then the factorials cancel. N plus 1 is positive, so the absolute value isn't going to do anything to it. And then the only thing that could be negative is this x term here. So the absolute value does have to stay on there. So when we simplify this, we end up with n plus 1 times the absolute value of x minus 3. So there's the gadget that we're going to use for our ratio test, simplified down. All right, so we've looked at what happens directly at the center. Now we're considering what happens everywhere else. Normally we don't do this because we know we're guaranteed to have convergence. Just wanted to show what that actually looks like. So we know at the center point we're guaranteed to have convergence. Normally when we do the ratio test, we're looking everywhere else. So we're making this distinction here that x does not equal 3. And that's important to note that if x does not equal 3, the absolute value then of x minus 3 does not equal 0. So keep that in mind because we're going to be looking at the limit of this in the next step. So now we do our ratio test limit. So we're going to do the limit of our absolute value an plus 1 over an as n goes to infinity. Let's fill in our simplified version. It's n plus 1 times the absolute value of x minus 3 as n goes to infinity there. And we want to calculate this limit. So x is a variable. We don't know what x is, but in the context of this limit, n is the thing that's changing. So if n is getting larger and larger, it's going to infinity. N plus 1 is going to infinity as well. And x minus 3 is not changing. It's fixed in the context of this limit. It's a constant. So we have this positive constant here times this number n plus 1, and as n gets larger and larger, n plus 1 is getting larger and larger as well. So this whole expression gets really big and goes to infinity. And why this is equal to infinity is because this absolute value x minus 3 term, we made note of it right over here. We're supposing that x does not equal 3, so that the absolute value of x minus 3 does not equal 0. And since the absolute value here is not 0, there's no stopping this n plus 1. So the only thing that could stop this n plus 1 from getting bigger and bigger is if this was equal to 0, but it's not. So this n plus 1 term is going to get bigger and bigger, and it's going to go to infinity overall. So we've calculated the limit for our ratio test, and so for x not equal to 3, what we're seeing here, the limit for our ratio test is infinite. So if we remember back to what the ratio test says, it means the series diverges. And it's diverging by the ratio test. So we've done the ratio test, and we've shown that no matter what x is, this limit gets really big, goes to infinity. And so the ratio test says that power series is always going to diverge, with that one exception. So we're always guaranteed to have at least one x value where the series converges, and that's because we're always going to have convergence at the center. So for all of those x values, the ratio test showed that it diverges except that one specific x value. So when we write down our radius of convergence and our interval of convergence, there's a few ways to write the interval of convergence here. There's only one x value, so we could write it as, getting carried away with my squiggles. Could write it as curly bracket 3. So this is just the set with one point in it, and so curly bracket 3. It's just the set with only one x value in it, or we could think of it kind of as like a collapsed interval. So it's the interval of just containing 3. So sometimes you might write it either way. This is general kind of set notation here, the curly brackets. So this is the set containing only that number 3. So our interval of convergence, we only have one x value where this thing converges. So our radius of convergence, what is our radius then? Well, again, think of the radius as sort of like half of the width. So the width of this interval is 0. Half of that is 0 as well. So the radius of convergence, r, is equal to 0. So this is kind of one of those odd examples that sometimes you see with power series where it just diverges for any x value except that center point. So we know we're guaranteed to have convergence at that center point. And you could do it for other series as well. You could kind of run through this similar calculation to see what happens at the center, and you would kind of end up just adding up a whole bunch of zeros. We can do that. That's no big deal. We can add up a whole bunch of zeros. Not an issue there. Where things get a little bit more interesting is what happens away from the center point. And that's where we use the ratio test. Normally, like I said, though, we don't show this part because it's just assumed that our power series is going to be converging at the center. So we normally just skip right to the ratio test, but I kind of knew there was going to be an issue on, so we started with that here. So normally you would probably start with the ratio test, just like we have, go through these steps, and then at this point you would see that it's infinite, with the exception this absolute value term could potentially be 0, in which case then you need to go back and investigate the center point. And we actually know it converges. All right, so just a kind of a little example there just to see kind of what can go wrong with a power series. All right, so next time we're going to, more power series coming our way. So we're in the power series unit, so we'll see kind of where to go next. But we'll be kind of investigating integration, differentiation of power series, a whole bunch of good things coming up. So we'll see you then. Bye-bye.